Welcome back to the deep dive. I had a bit of an existential moment on my way to the studio this morning.
Oh, yeah.
Yeah, I was walking down the sidewalk, checking my watch, and I realized I was moving at roughly 3 miles per hour.
Nice.
And it just hit me. That is the default human speed.
Yeah.
For the vast, vast majority of our history as a species, we're talking hundreds of thousands of years. That was it. That was the speed limit.
That was the universal constant.
Exactly. If you wanted to go somewhere, you walked.
Mm.
If you were in a hurry, you ran, which maybe gets you up to 15 miles per hour for a very short burst before you completely collapse.
And if you were wealthy or maybe just lucky, you got to sit on top of an animal that walked slightly faster than you.
Yeah.
But essentially, the world was defined by biology.
Yes.
The horizon was a real limit, and it was dictated by how many calories you could burn before the sun went down.
Our geography was local because our feet were slow.
Yeah.
And then in just this tiny, tiny sliver of human history, really just the last 2 centuries, we completely broke reality.
We did.
We went from walking speed to the speed of sound. We went from being a local species to a global one, and we did it by building these incredible machines that roar and float and fly.
It is a violent acceleration when you look at it on a timeline. It's almost a vertical line of progress. And that is exactly what we are unpacking today. We aren't just looking at cars or trains in isolation. We are looking at the entire ecosystem of movement.
We are doing a deep dive into cars, trains, ships, and planes, a visual encyclopedia of every vehicle. It's this massive visual history by Clive Gifford, and it's published in association with the Smithsonian. And I know the word encyclopedia might make you think of, dusty library shelves.
Right, something very dry.
Yeah, but this is something different.
It is. It's a chronicle of human restlessness. It's the engineering story of how we just refuse to stay put. What I love about this source material is that it doesn't just give you the specs, though it has plenty of those. It gives you the context.
The stories behind them.
The stories. It tells us about the failures, the explosions, the traffic jams that lasted for days, and the sheer audacity of the engineers who looked at a steam kettle and thought, you know what? I can make that drive.
So the mission for this deep dive is to trace that arc. We want to unpack the evolution of transportation, not just the nuts and bolts, but the human drive to go faster, to go further and deeper. We want to understand how we got from a world where you were born and died in the same village to a world where you can wake up in London and go to sleep in New York.
And before we get into the heavy machinery, we have to talk about the author, Clive Gifford. There's a backstory in the foreword that I think frames this whole discussion just perfectly. This isn't just a job for him. It's hereditary.
It really is. His father wasn't just, a commuter. He was a pilot. He flew gliders and worked for an early airline company. So Gifford grew up around the smell of aviation fuel and the sound of propellers.
The text mentions his father worked for a company that offered many people their first taste of air travel. If you really think about what that means, that moment in the mid-20th century where humanity collectively lifted off the ground for the first time, it's profound.
It's a fundamental shift in perspective.
But for Clive, the pivot point, the moment where the obsession really solidified, was when he was 11 years old.
The air show. I feel like a lot of kids have that core memory. The noise, the spectacle.
Exactly. He remembers his father taking him to see this incredible array of aircraft, and the contrast is what stuck with him. On one side of the tarmac, he saw these massive jet bombers.
The peak of military power at the time.
Immense power. Machines designed for destruction, sleek, and just terrifying. And right next to them, he saw these nimble aerobatic biplanes designed for, dancing in the sky.
But, and this is the part I love, he wasn't just looking up at the sky. He turned around.
He looked at the parking lot.
He looked at the parking lot.
And he says he was just as fascinated by the giant trucks and the 2 Ferraris parked in the lot as he was by the bombers.
That is such a specific, perfect detail. 2 Ferraris at an air show. But it completely captures the theme of the book. It's this universal fascination with machines that move.
Yes.
It doesn't matter if it floats or rolls or flies. If it has an engine, it goes fast, it captures that imagination.
It's that realization that engineering on the ground is just as miraculous as engineering in the sky. So let's start where the book starts. Let's start on the ground.
All right, the road to modernity.
Yeah.
Now, when I think of the first car, my brain, it just defaults to the Model T or maybe a Benz if I'm trying to sound smart.
Yeah.
But the timeline in this encyclopedia, it pushes it back Way, way further than I expected.
Oh, way further. We are talking about the 18th century.
The 1700s.
1769, to be exact. That is before the American Revolution was even wrapped up. Napoleon wasn't even emperor yet.
And it wasn't a Ford, it wasn't a Benz. It was a French inventor named Nicholas Joseph Cugnot.
Cugnot. And he built what is technically the first working automobile. But if you are picturing a car in your head right now, you need to just delete that image.
I am looking at the visual in the source material. It looks like a giant wooden tricycle that crashed into a giant copper brewery vat.
That is a painfully accurate description. It was called the Fardia à Vapeur à Steam Dray. It was designed for the French military.
For what purpose?
Specifically for hauling heavy artillery cannons. The vat at the front that you mentioned is actually the boiler.
And this design really highlights the problem with early steam tech, doesn't it?
It does. It was an external combustion engine. You burn wood to boil water to make steam to push a piston. It's incredibly heavy. It's inefficient. And in Cugnot's case, it made the vehicle just disastrously front-heavy. The boiler hung over the single front wheel.
Which was also the steering wheel.
Yeah. Exactly. So you have the heaviest part of the entire vehicle hanging off the one part you're trying to turn.
Oh, that's a nightmare. Imagine trying to steer that thing.
It was incredibly difficult to maneuver. The weight of the engine is literally fighting you every single inch of the way.
And the specs on this thing. They're hilarious by modern standards. What was the top speed?
The top speed of the Cugnot steam cart was a blistering 2.5 miles per hour. That is 4 kilometers per hour.
So going back to my intro, I walk faster than the first car drove.
You could briskly walk alongside the world's first car and probably beat it to its destination, and you'd be safer too.
Safer.
The book mentions that on one of its test runs, it reportedly crashed into a stone wall because it had no brakes.
Of course it didn't. Why would you need brakes when you're going 2.5 miles an hour?
Well, I guess the wall would disagree. But we have to give Cugnot credit. It was self-propelled.
Right. That's the automobile. It moved without a horse. It started everything. It proved that we could divorce movement from muzzle.
It was the proof of concept.
So we have this steam-powered artillery kettle in 1769. But the real revolution, the one that leads to the car sitting in my driveway right now, that relies on a different kind of explosion. We have to talk about the internal combustion engine.
This is the heartbeat of the modern world. The timeline in the book highlights 1876. That is when a German engineer named Nicholas Otto builds the first practical internal combustion engine.
Okay, so for the listener who might not be a mechanic, why is internal such a massive leap from Cugnot's external steam power?
It comes down to efficiency and, more importantly, size. With steam, you have a firebox, you have a huge boiler, you have water, you have pistons. It's heavy, it's dangerous, and it takes a long time to start up. You literally have to wait for the water to boil.
Right, you're building a head of steam.
Exactly. With internal combustion, the explosion happens inside the cylinder. You mix fuel with air, you ignite it with a spark, bang, the piston moves. It provides immediate power in a much, much smaller, lighter package.
And once you shrink the engine, you can fundamentally change the vehicle it goes into.
You can. You don't need a massive heavy cart anymore. So in 1885, Carl Benz takes this engine and puts it on a 3-wheeled chassis, the Benz motor wagon.
And this is what we consider the first true car.
This is widely considered the first true car. It's the great-grandfather of every single vehicle on the road today.
And not just cars, right? The source mentions that shortly after, in 1894, we get the Motorrad.
The Hildebrand and Wolfmiller Motorrad, the first production motorcycle. It's fascinating that the divergence happened so early. Engineers immediately realized this power plant was scalable.
You could build different things around it.
You could put it on a carriage to make a car, or you could strap it to a reinforced bicycle frame to make a motorcycle. The possibilities just exploded.
But here's the thing. All of these early machines, the Benz, the Motorrad, they were novelties, right? They were toys for the rich or, experiments for engineers. If you saw one in 1895, you probably laughed at it. They weren't transportation for the average person yet.
No, not at all.
That didn't happen until 1908.
The year of the Model T.
The Ford Model T. Now, we always hear about the assembly line, but was that really the only thing that mattered? I feel like there has to be more to it.
The assembly line gets the credit, and it was revolutionary, of course. But the real revolution behind the assembly line was interchangeability.
What do you mean by that?
Before Ford, cars were hand-built. If a piston broke on your 1899 Panhard, a craftsman had to individually file a new one to fit that specific engine hole. Every car was bespoke.
So every part was unique to that one car.
Exactly. Ford changed the process. He made parts so precise that a piston from car A fit perfectly into car B and C and D.
That sounds so simple to us now, but that must have been a manufacturing revelation.
It was. That standardization, combined with the moving assembly line, crashed the price. It went from a rich man's hobby to a tool for the average farmer or the factory worker. It democratized mobility.
And it changed the geography of where we could live. Suddenly, you didn't have to live right next to the factory or the farm anymore. You could commute.
Precisely. It created the modern concept of the road trip and the suburb. It redrew the map of society.
So we go from walking 2.5 miles per hour next to a steam cart to driving a Model T at maybe, 40 miles per hour. But humans are never satisfied with just getting there. We have this innate need for speed. The source material has a whole section on record breakers, and the numbers are just mind-boggling.
They really are, and it's so interesting to track the jump in speeds just to see how quickly the engineering advanced. Let's look at 1927.
Okay, 1927, the Roaring Twenties. What's the record?
The vehicle is the Napier-Campbell Bluebird, and it sets a land speed record of 195 miles per hour.
Wow.
That's 314 kilometers per hour.
195 miles per hour in 1927. That is terrifyingly fast for the technology of the time. The tires alone must have been barely holding together.
It was an incredibly dangerous pursuit. I mean, aerodynamics were still basically guesswork. But then, fast forward to 1997, we are jumping 70 years into the future.
To the Thrust SSC, I remember this.
The Thrust SSC. Now compare 195 miles per hour to this. The Thrust SSC hits 763 miles per hour.
763.
That is 1,228 kilometers per hour.
That's breaking the sound barrier.
On land.
That's the key. This isn't a plane diving from 30,000 feet. This is a car, well, yeah, I'm using the word car, very loosely, driving across the Black Rock Desert faster than the speed of sound.
And loosely define is exactly right. The Thrust SSC is essentially two Rolls-Royce jet engines, taken from a Phantom fighter jet strap to a chassis. It didn't drive the wheels, the jet thrust pushed it.
So the engineering challenge there isn't just about raw power, is it? It's about control.
It's entirely about control. The challenge is keeping the thing on the ground. At supersonic speeds, shock waves form. The air wants to get under the vehicle and lift it up like a wing.
So the problem shifts from how do we go fast to how do we not accidentally fly?
Precisely. Now, that's a pure record-breaking machine, a rocket car. But what about a car you can actually buy, if you have a few $1,000,000 lying around?
The source points to 2005 for that particular milestone. The Bugatti Veyron.
The legendary Veyron. It set the record for the world's fastest production car. It clocked 253 miles per hour.
Which, seems almost slow compared to the Thrust SSC, but you can drive the Veyron to the grocery store.
And that's the crucial difference. The Veyron needs air conditioning. It needs turn signals and airbags. It needs an engine that doesn't melt after one run. Making a car go 250 miles per hour while keeping the driver comfortable in leather seats is arguably a harder engineering challenge than just strapping a jet engine to a sled.
It really highlights that split in engineering philosophy.
Yeah.
You have the record breakers, which are pure physics experiments, and then you have supercars, which have to actually function in the real world with all its rules and regulations.
And speaking of the real world,
Yeah.
as the cars got faster and more numerous, the world around them had to adapt. And usually, the world wasn't ready. The source material has some hilarious and kind of terrifying examples of these infrastructure growing pains.
Oh, my absolute favorite story in the whole book is the traffic light story.
It is a classic example of trial and error, a very explosive error.
So 1868, London. The streets are absolute chaos. You have horse-drawn carriages, early pedestrians, people pushing carts. It's a total mess. They need a system.
Right. So they install the first traffic lights near Parliament. But you have to remember, this is 1868. They didn't have electric LEDs.
So what did they use?
Gas. These were gaslit semaphore signals operated by a police officer.
Gas lights. In the middle of a busy intersection. I think I see where this is going.
And just a few weeks after installation, they exploded.
It blew up.
They blew up. Imagine being a Victorian Londoner. You see this newfangled safety device designed to bring order to the chaos, and suddenly, boom! Book said it actually injured the police officer who was operating it.
It's a perfect metaphor for the messiness of innovation. We build the tech before we fully understand how to control it.
Exactly.
And speaking of chaos, we have to talk about traffic. We think traffic is bad now. But the source mentions a record-breaking traffic jam that just puts my morning commute to shame.
The world's longest recorded traffic jam, 1980, France.
A Paris-Lyon jam.
The Paris-Lyon jam. How long do you think it was?
I don't know, maybe 30 miles,
40.
105 miles long,
No.
170 kilometers of bumper-to-bumper stationary metal.
105 miles. That is like a traffic jam stretching from New York City all the way to Philadelphia and then keeping going. I can't even fathom that.
Can you imagine the frustration, the sheer hopelessness? It really shows that while we got very good at building the machines, the cars, the trucks, we struggled to build the infrastructure to hold them all. We created these freedom machines and then immediately stuck them all in a 105-mile prison.
But innovation always tries to solve the problems innovation creates. The timeline mentions a British company called Flash Park in 2013 inventing something called a talking parking ticket.
Which is just bizarre, but it shows that we are constantly trying to use technology to manage the swarm. Whether it's exploding lights or talking tickets, we are always trying to tame the beast we created. So we've covered 4 wheels. But the Encyclopedia also spends a good chunk of time on 2 wheels. And honestly, the evolution of the bicycle is way more connected to the car than I ever realized.
It is incredibly connected. In fact, you can make a strong argument that without the bicycle, the car would have taken much, much longer to develop.
Okay, let's break that down. The book starts with the high wheeler in 1871. This is the penny farthing, right? The iconic one.
Yes, the one with the gigantic front wheel and the tiny little back wheel.
Why did they look like that? Was it just for style? Or was it some kind of status symbol?
No, it was pure simple physics. In 1871, they didn't have gears. They had direct drive. The pedals were attached directly to the hub of the wheel.
So 1 rotation of your feet equaled 1 rotation of the wheel.
Exactly. So if you wanted to go fast, the only way to do it was to make the wheel huge so that one pedal stroke covered more ground.
So your top speed was literally limited by the length of your leg.
Basically. And it was incredibly dangerous. If you hit a small rock or a pothole, you were falling from a significant height, often face first over the handlebars, hence the old term, taking a header.
Right. But then comes 1880 and the safety bicycle. This changes everything.
And this is the key moment. The safety bicycle, the Rover, was a popular one. It introduced the pedal and chain mechanism.
It's chain.
The chain drive. This allowed you to have gears. You could have 2 wheels of the same size, but still go fast because of the gear ratio. This made cycling safe and accessible for everyone, not just daring young men. But crucially, that chain drive technology directly influenced early car designs.
How so?
Well, the first automakers faced the exact same problem. How do you get power from the engine to the wheels? They just borrowed the solution from the bicycle. Many early automobiles were chain-driven.
So the bicycle was the prototype for the modern car's transmission of power.
Exactly. And the tires, too. John Boyd Dunlop invented the pneumatic, the air-filled tire, for his son's tricycle. Without air-filled tires, early cars would have rattled themselves to pieces on cobblestone streets. The car really stands on the shoulders of the bicycle.
Now, cycling eventually splits. It goes from being just transportation to being a sport, a lifestyle. The timeline mentions 1981 and the stump jumper.
Ah, the birth of the mountain bike.
That was the first one.
The stump jumper went on sale in the USA as the first mass-produced mountain bike. Before this, people in California were modifying old beach cruisers to go down hills. They called them clunkers. But the stump jumper marked a real shift where bicycles became specialized tools for adventure, not just for getting to work.
Specialization is a huge theme in the book. We see vehicles designed for very specific, sometimes very intense tasks, like war.
War is a massive, if unfortunate, driver of transportation technology. Conflict demands performance. If your vehicle fails in war, you don't call a tow truck. You lose the battle.
The source brings up the tank, a really iconic example.
1916, World War I, the British Mark I.
And it goes into battle in France. This is the first fully working armored tank.
And if you look at the images of these early tanks, they are absolute monsters. They were designed to solve one specific problem, the trench. The brutal stalemate of the Western Front. They needed something that could cross a wide ditch, crush barbed wire, and deflect machine gun fire.
And they changed the landscape of warfare completely.
Overnight. And then in World War II, we get something smaller, but maybe even more iconic, the Jeep.
1940. The Jeep is introduced as a general-purpose light truck. And general purpose is the key phrase there.
It is. Is that where the name comes from? GP, Jeep.
That's the prevailing theory, yes.
Yeah.
GP slurred together becomes Jeep. And it could do anything. It could carry wounded soldiers, tow guns, move officers over the roughest terrain. It was the grandfather of the modern SUV. It proved that a vehicle could be rugged, simple, and go anywhere. Speaking of going anywhere and rugged vehicles, we have to talk about 1979.
I know exactly where you're going with this.
Bigfoot.
The first monster truck.
Bob Chandler developed it. And I just love that this is in a Smithsonian Encyclopedia. You have the Model T, you have the Space Shuttle, and you have Bigfoot.
It absolutely belongs there. It represents a different kind of human drive, the drive for pure entertainment, for spectacle. Taking a Ford F-250 and putting massive agricultural tires on it just to see if it can drive over other cars. That is a very specific, very human type of innovation.
It's the hold my drink and watch this school of engineering.
Precisely. But amidst all this fun and war, there is a really serious side. The book introduces us to a character named Sierra Sam.
Sierra Sam, 1949. Who was he?
He was the first fully formed crash test dummy.
Okay, so why does this matter in a book about vehicles? It's not a vehicle itself.
Because it marks a fundamental shift in philosophy. For the first 50 years of the car, the focus was entirely on does it run and how fast does it go? With Sierra Sam, the focus shifted to is it survivable?
It marks the beginning of the entire era of safety engineering.
Exactly. We stopped just looking at the machine and started looking at the fragile human inside the machine. Without Sierra Sam and his descendants, we wouldn't have seatbelts, airbags, or crumple zones. He's an unsung hero of the automotive world.
So we have conquered the road with cars, bikes, and monster trucks. But before the car ruled the world, there was another king, the Iron Horse.
The train.
Part 3 of our dive is Riding the Rails. And the history here is deep. We are going back to the steam era again.
Steam is where it all begins for industrial-scale movement. We mentioned 1769 with Cugnot, but stationary steam was already happening. In 1770, James Watt invents the compound steam engine, but it takes a while to put it on wheels effectively.
The timeline mentions 1804 for the first one.
Right. Richard Trevithick builds the Penny Darren. But here is a crucial detail. This wasn't for people.
This was for mines, wasn't it?
Yes, it was a purely industrial tool. It was designed to haul iron and coal out of the earth. The first trains were basically just better conveyor belts. They were about moving raw materials, not passengers.
But then comes the rocket.
1829, Robert Stephenson's rocket. This is the design that set the standard for the next century. It set new speed records, and more importantly, proved that steam locomotives could be fast and reliable enough for regular service.
And almost immediately, they started connecting cities. 1830, the Liverpool and Manchester Railway begins, the first intercity service in the world.
And that changes the human perception of distance. Suddenly, Manchester and Liverpool aren't distant neighbors separated by a long, bumpy carriage ride. They are connected. It collapses space and time.
But the ambition didn't stop at connecting two cities on the surface. They wanted to connect everything, even under the ground.
The London Underground, 1863. The Metropolitan Line opens.
I have to stop on this point again because it just blows my mind. 1863, that is the middle of the American Civil War. Abraham Lincoln is president, and London is opening a subway system.
It is incredible, but you have to remember, these were steam trains.
That's what I can't wrap my head around. Steam trains. Underground. In tunnels. How did that even work?
It was exactly as bad as you imagine. It was smoky, it was dirty, it smelled of sulfur and soot. They called it the sewer. People would come out of the stations covered in a thin layer of grime.
So why on earth did they do it?
Desperation. London was the biggest city in the world, and it was choking on its own traffic. The streets were gridlocked with horses and carts. They had no choice but to dig down. It was a desperate but brilliant solution to urban congestion.
And while London was digging down, America was building across.
1869. The Transcontinental Railroad is completed.
1,907 miles of track.
It physically united the United States. Before that, getting to California was a dangerous month-long journey by wagon train or a very long sea voyage around the tip of South America. After the railroad, it was just a ticket. You could cross the continent in days.
It created a national identity in a way that wasn't possible before.
It did, and the scale just keeps getting bigger. The source mentions the Simplon Tunnel in 1906, connecting Italy and Switzerland by drilling straight under the Alps.
Just drilling through a mountain range.
And then the Trans-Siberian Railway in 1916, the world's longest railroad line, 5,772 miles.
Wow.
That's 9,289 kilometers. It crosses an entire continent, from Moscow to the Pacific Ocean. It just shows the sheer force of will required to lay steel across that much earth.
But trains couldn't stay on steam forever. Just like with cars, we see the shift to electric.
We do. It starts small in 1881 with the first electric streetcar service in Germany, but the real leap comes much later with the bullet train.
The Shinkansen.
Japan, 1964. This redefined what a train could be. Before the Shinkansen, trains in many parts of the world were seen as dying technology, being replaced by cars and planes. Japan proved that if you built dedicated tracks and focused on speed and punctuality, rail could compete.
So it wasn't just a faster train, it was a dedicated high-speed system.
Exactly. It connected Tokyo to other major cities, and it looked like the future.
And speaking of the future, we have to talk about maglev.
Magnetic levitation.
The concept sounds like pure science fiction. Trains that float on air.
It was developed by a German inventor named Hermann Kemper. The concept is to use powerful electromagnets on the train and the track to repel each other, lifting the train millimeters off the guideway. This eliminates friction.
No wheels touching the ground at all.
No wheels, no rolling resistance. The only thing slowing it down is air resistance.
The source mentions a UK milestone here. The first commercial maglev in Birmingham.
Yes, it was a short link from the airport to the train station, a relatively low-speed shuttle, but it proved the tech worked commercially day in and day out. But for the real speed, we have to look at the tests.
Japan again.
Yes, a passenger-carrying test run hitting 373 miles per hour. That is 600 kilometers per hour.
373 miles per hour. On the ground, that is faster than the takeoff speed of most passenger jets.
Much faster. At that speed, the landscape is just a blur. It's almost abstract.
And even on conventional rails, not even maglev. The French TGV hit 357 miles per hour at test.
We have pushed the technology of steel on steel and magnets on air to limits that Cugnot with his 2.5 mile per hour cart couldn't have even dreamed of.
It is a staggering progression. Now, one thing the book does really well, because it is a visual encyclopedia, is help you visualize the scale of these machines. Because numbers can get abstract. 100 feet long doesn't really mean much to my brain.
The scale boxes! I love this feature.
Yes. Throughout the book, there are these little graphics that compare whatever vehicle they're showing to either a standard child or a standard school bus.
It's such a simple but incredibly effective tool, because we all have a mental image of how big a school bus is.
The constants they use are a child who is 4 feet 9 inches, or 1.45 meters, and a school bus, which is 36 feet long, 11 meters.
Right. So let's look at some of the comparisons. Take the PLP-50.
The PLP-50. I love this little car. It's in the mini motor section.
It is the smallest production car ever made. And if you look at the scale box for the PLP-50, it's just hilarious. The car is barely bigger than the child standing next to it.
It looks like a suitcase with wheels. You wear it more than you drive it.
It basically is. You could fit several of them inside the school bus. The book mentions it didn't even have a reverse gear. If you wanted to back up, you had to get out, grab a handle on the back, and pull it like a wagon.
And then you flip the page and you see the crawler transporters. These are the machines NASA used to move the space shuttles to the launch pad.
And the scale box there is completely different. The child is just a speck. Even the school bus looks like a tiny toy car next to it. These machines are moving buildings, basically. They are the largest land vehicles ever built.
The book also asks us to visualize some very specific, often beautiful vehicles. One that stood out to me was the Didion-Bouton Typo.
Ah, the vintage style, that early 1900s look.
It just looks so elegant. It has that open-air carriage look, brass lamps, spindly wheels. It reminds you that cars used to be luxury items, almost like jewelry or fine furniture.
And you can contrast that directly with something like the John Deere 650K XLT.
The crawler dozer.
Pure utility. Bright yellow, massive tracks, a blade that can literally move mountains. It's not about elegance, it's about raw power. It's a tool.
Or the Sea-Doo Spark.
The personal watercraft. Bright colors, molded plastic composites. It's about pure fun. It's a toy for the water. And it shows how material science changed from wood and steel to lightweight polymers.
And we can't forget the Montgolfier hot air balloon. The visuals in the book are incredible.
The visuals on that are stunning. It wasn't just a functional balloon, it was an art piece. Highly decorated gold and blue fabrics. It shows that when we first ventured into the sky, we wanted to do it with style. We wanted to impress the gods.
Which brings us perfectly to part 5 of our deep dive, water and air. The book calls this the global village aspect of transportation.
Because that is what these technologies created. They shrank the planet, they stitch it together.
Let's start with the water. The foreword makes a really good point about shipping. We don't think about it much. We see trucks on the highway, we see trains, but shipping is almost invisible to most of us.
But it is the single most important link in the global chain. Shipping connects the continents. It allows us to buy food grown on the other side of the world for pennies.
That banana I had for breakfast this morning.
That banana is only in your kitchen because of shipping. The modern container ship is the absolute backbone of the global economy. It turned the chaos of loading and unloading cargo into a standardized, efficient Tetris game.
But the source reminds us that it wasn't always this safe, organized, logistical ballet.
Not at all. It mentions pirates.
Pirates. The book explicitly brings up the dangers of early sea travel, specifically pirates plundering Spanish treasure ships coming from the New World.
It's a great reminder that the ocean is a hostile environment. We have tamed it with massive steel ships and GPS, but the history of water travel is a history of immense risk. And pirates are still a very real thing today, which shows that some things don't change.
And speaking of risk, we have the conquest of the air.
This brings us right back to Clive Gifford's dad, the gliders.
The glider is really the purest form of flight, isn't it?
It is. There's no engine. It's just you and aerodynamics. You are literally surfing the air currents. It requires a real intuitive feel for the atmosphere.
But the timeline moves us quickly to machines with engines. The book shows a Booker Bow 133C Youngmeister.
That is a mouthful.
It is. But it's this beautiful machine, an aerobatic biplane.
This represents that era where flight became something you could master, something you could do tricks with. It wasn't just about staying airborne. It was about dancing in the sky. It was the era of the barnstormer.
But then, of course, the engines get bigger. We get jet fighters.
Speed again. Always speed. But also surveillance. The book has a section called Eyes in the Sky.
That's a fascinating angle. Planes aren't just for moving people or dropping bombs. They are for gathering information.
In the modern world, looking down is just as important as flying forward. The U-2 spy plane, the SR-71 Blackbird, these vehicles were built to see without being seen, to fly on the edge of space.
And finally, the ultimate destination, space.
The book touches on launch vehicles and space probes. This is where the whole transportation theme reaches its logical limit. We are no longer just moving across the Earth, we are leaving it.
Leaving the planet entirely. It's the logical conclusion of that drive to go further. We filled in all the blank spots on the map, so we had to go off the map.
Exactly. The Voyager probes are still out there, carrying our history into the void. The ultimate road trip.
So we have covered a lot of ground and water and air. We've gone from 1769 to the modern day, from 2.5 miles per hour to supersonic speeds.
It is an absolutely incredible acceleration of progress.
If you look in the summary of this journey, we started with a steam cart that was basically a big kettle on wheels.
On a mine train pulling coal out of a hole in the ground.
And in roughly 200 years, a human lifetime repeated only a few times, we ended up with the thrust SSC going 763 miles per hour and maglev trains floating at 373.
It is a blink of an eye in evolutionary time. We are apes that learn to fly supersonic.
And we have the Smithsonian preserving all of this. That's the other key takeaway from the source. The Smithsonian isn't just a museum, it's a repository of our history. The book mentions they have 137 million artifacts. They are keeping the evidence of this journey safe for all of us.
It's comforting to know that Sierra Sam and the early steam engines and even a Keel P-50 are being looked after.
They are the milestones of our species' restlessness.
They are.
So here's where I want to leave the listener today. We've talked about the talking parking ticket and the exploding traffic light.
Innovation is messy.
It is messy, and it's sometimes just plain weird. But it moves incredibly fast. We went from steam carts to maglevs in 200 years.
It really is an exponential curve.
So here is the question for you to think about. If we look at this trajectory, this exponential curve of speed and connectivity, what does the visual encyclopedia of every vehicle for the year 2126 look like?
That is the question.
Are we still on the road? Are you still using wheels? Or have we moved past them entirely? Are we teleporting? Are we shooting through vacuum tubes?
Or, and this is another thought, or have we decided to slow down? Maybe the future isn't about more speed, but about more sustainability. Maybe we go back to the bicycle, but a high-tech electric assist version of it.
That's a fascinating thought. Maybe the internal combustion road was just a phase we were going through for a couple of centuries?
It does make you wonder.
Well, thank you for joining us on this deep dive into the machines that move us. It's been a wild ride.
Always a pleasure.
Drive safe, watch out for exploding traffic lights, and we will catch you on the next one.